Hey everyone, welcome to another edition of Fermion Live Code Tuesdays. My name is Sohan Maheshwar. I'm joined by Radu, and today we are going to talk about putting SpinKube on a SpinKube. This is a very intentional sort of title that we've chosen. So just to give you a bit of background, in KubeCon a couple of weeks ago, we carried a Raspberry Pi cluster and we put SpinKube onto that, and we had some fun with it. Radu even carried it on stage, which is a story we will get to in a little bit. So yeah, today we are going to show off, or Radu is going to show off how we actually built this and some cool things related with it. See some familiar names in the audience. Hey, Vamshi, Rajat, Adam. Also, Sebastian's here. Sebastian is a dev advocate at Avon. Fantastic guy. Also does a bunch of live streams, and we will be live streaming with him very soon as well. So keep an eye out for that. Radu, the man of the hour.
Hello.
Yeah. So yeah, I think you had some fun with the Pi cluster that you built, right? Do you want to start talking a little bit about it?
Sure. This is the as you mentioned, yeah. For KubeCon, we put together a Raspberry Pi cluster running SpinKube, which is our the new open source project that we've been working on together with Liquid Reply, SUSE, Microsoft, and a few others. And to showcase SpinKube and to showcase how exactly you can run WebAssembly on Kubernetes and the benefits of it and how to get started, we basically decided it would be a good idea to actually build a tiny cluster that's more constrained than what you would normally find in a cloud somewhere, and basically run SpinKube, show a couple of the things of what SpinKube can do, and of course, I really love a good pun, and so SpinKube running on an actual cube that has a bunch of spin logos, and so the puns kept writing themselves at that point, and so yeah, it is. I'm looking at the slide because it is right here, so I'm gonna try and okay, let me.
Nice.
Can you actually see it?
Yes, we can.
Okay.
Yeah.
So this is a 5-node Raspberry Pi cluster. So these are Raspberry Pi 5s assembled in an acrylic cube with an integrated power supply that's running right here. Oh. And then a fan that keeps everything cool. This is running for around a couple of hours now, and it's at like 35, 36, 37 degrees Celsius, which is excellent. Also, I hope the fan is not too noisy. It is quite loud and noticeable here, but hopefully it's not. You can't hear it. And then this also has an integrated network switch, which connects every single board to this, and then this gets connected to my computer right here. So there's basically just one power cable and then one network cable connecting everything here. So this is the cube, as I mentioned, Raspberry Pi 5s. I was very lucky to actually get my hands on Raspberry Pi 5s because they were out of stock for a very long time, and so the moment I saw they were in stock, I just ordered 5 of them. So I'm very
As one does.
actually got them in stock. Yeah. So
Yeah.
I'm glad I managed to.
Nice.
Oh, Nuno's here.
Hey, Nuno. How's it going, Nuno? Yeah, so Radu showed you the beast, as Rajat calls it. It's a super cool device, and honestly, at KubeCon as well, we just had it at our booth, and so many people were very curious about it. Many people had played with it; they had their own. So we thought we'd do a live stream, and Radu could show us the step-by-step on how we actually went about, building this. First question I need to ask you, Radu: was it easy to get this past airport security?
Thankfully, I did not have to get it past airport security. I took the train from home to KubeCon Paris, so I did not have to go through TSA or any airport security. So I don't know whether it would be allowed to get through airports. I think you should be, but then again, I wouldn't want to try it.
Yeah. I mean, trying to explain like, oh, this is a Raspberry Pi cluster, but look at it, it has a data switch and it's so cool and all of that. To airport security is not something I look forward to, but good you took the train.
Yeah, thankfully there's no train security that you have to pass through. So
yeah. Awesome. Yep. Cool. So I think, folks, we can maybe just get started. We have a lot to cover today because, well, there is a bit of the setup of the cube as well as the SpinKube stuff. So yeah, let's just get straight to it.
Thank you, Bunny. Yes, I mentioned this is running at probably 36, 37 degrees Celsius, and that's currently 96.8 Fahrenheit
Yeah.
for our friends across the pond who don't use the right
The right.
measurement.
My hot take, and we try not to be controversial here, but my hot take is that, and it pains me to say this, but I think Fahrenheit might be better to describe like the temperature and how a person feels as opposed to like scientific, right? I think there's more of a range. Anyway, that is my super controversial take for the day. I'm done.
Oh no, you're breaking up. Sorry. Okay.
Yeah. All right, Radu. So enough of the hot takes. Let's just get to the cool stuff.
Sure. So as I mentioned, 5 Raspberry Pi 5s. These the cluster itself, the main parts were sourced from picocluster.com, which had everything in stock. These are, as I mentioned, Raspberry Pi 5s. They're 8 GB of memory, 4 cores each, put together in this cube. And I have a link that I'm going to share at the end with a gist that goes through the entire setup that I'll briefly go through right now. Feel free to interrupt me if there are any questions, Sohan. I'm not able to see the screen right now. So if there are any questions, feel free to interrupt me at any point. And yeah, let's go through exactly how I put this together. So I mentioned, because this has an integrated power source and a switch, instead of having to plug it in 5 times and have 5 network cables that I have to put in and plug in everywhere, this basically has one power cord and one Ethernet cable, which is extremely uh, much better compared to the alternative, which meant I could get this on a train and then set it up at the booth, just plug it in twice, and that was it. You can directly plug it into your laptop. There's a way in which you can configure your laptop to give an internet connection to this, which means you don't even have to plug it into a router. And I can detail that at some point if people are interested in. But very, very elegant compared to what I did in the past with Raspberry Pis, where I had a cluster of cables that I had to figure out where to plug in. And so, highly recommend Pico Cluster. And oh, look, Raspberry Pi 5s are now in stock. So good to know. So because you get a bunch of things, you can either get it assembled if you want to, or you can get it by parts and then you put everything together. You have to first put it all together. You'll have instructions here if you want to. Once you assemble the actual acrylic panels and you put together the boards and the fan and the network switch, you have to configure an operating system. The goal of this is to run SpinKube and Kubernetes. Before you can do any of that, you have to flash an operating system. You have to configure it. You have to make sure they're all on the same network. So this, the next couple of minutes, we'll walk through that process. So first and foremost, you have to put an operating system. Raspberry Pi is a full one board computer, so it runs full Linux. You can, if you're interested in, there are instructions on the Raspberry Pi blog on how to do net booting. So instead of flashing your operating system on an SD card, you can boot directly from the network. I did not do that. There are various guides and tutorials that show you how to do that if you want to. I wouldn't. I didn't have the time to set everything up. So first, you'll have to go on and get a Raspberry Pi compatible operating system. The main prerequisite for running WebAssembly with SpinKube is it has to be a 64-bit operating system. That is because SpinKube is built on top of Spin, which is built on top of Wasm Time, and Wasm Time currently requires a 64-bit operating system. I'm using the Raspberry Pi OS Lite, 64-bit. You can use Raspbian OS. You can use directly Debian. It really, as long as it's a 64-bit Linux ARM64 operating system, you should be good to go. I really just went with Raspberry Pi OS Lite because it's a recommended 64-bit operating system for this. If you want to use the GPIO, the general purpose input output pins, you probably need a Raspberry Pi specific operating system like Raspbian, just because it has everything set up. In this case, I'm not using any of it, but I might just experiment at some point with like devices and stuff like that. So Raspberry Pi OS Lite 64-bit is a very good choice there. Then you have to, after downloading the operating system, you'll have to flash each SD card at a time. Each of these 5 boards has their own micro SD card, and you have to just flash the operating system. Basically, get the Raspberry Pi imager and set every micro SD card, flash the operating system, and then put it in the board. This is the step where it makes sense to go ahead and give a host name for each of the boards, connect automatically to like Wi-Fi credentials and the Wi-Fi network, and add an SSH key because you will have to SSH at a later step. And so this is the step where you'll have to configure the sort of boot step and configure booting process for your each of the boards. So I gave them the name Pi 0 to Pi 4, which is going to be reflected because that's the host name. Those are going to be my node names later on when I do Kubernetes on this cluster. So once you flash the SD card, configure the Wi-Fi access if you need to, SSH key and everything else, insert the SD card into the Pi board, and then hit the power switch. There's a tiny switch here that powers everything on. It goes through the integrated power source, and then each of the boards is connected to this one. Once you flip the switch, they'll start booting. Assuming the boot was successful and assuming your boards are actually connected to your network, this is the step where it's kind of finicky and it's very dependent on your own setup. The reason why I mention configuring Wi-Fi credentials is because depending on the setup, it would be potentially helpful to connect over Wi-Fi while doing all the setup if you don't have access to a router. In case you missed it here, I don't actually like this is directly connected to my computer. There's no router involved here, so depending on how your setup looks like, you might have to.
Radu, so
Yeah,
not sure if it's just me, but your video seems to have paused. Maybe you hit the pause button on your iPhone.
I think I did.
Okay.
Give me a second.
Yeah. I've been there. So yeah, there we go. It's back. Yeah.
Okay. I'm not going to show the cluster again, but yeah, there we go. Depending on, as I mentioned, I don't have it. I don't have any Ethernet cable plugged in directly in a router, which means I benefited greatly in the beginning in the big first setup from having each board individually connected to Wi-Fi. So I am in the process to set up everything up. Finding devices on your local network was very helpful for me. So I'm using ARPScan, which is a tiny utility that gives you the IP addresses and MAC addresses for all the devices on your network. And basically, assuming you configured your SSH key properly, and when you flash the operating system, you should now be able to boot into to your cluster. So assuming everything worked well and assuming you're pointing to the right SSH key, you should be able to log into your cluster. So because this is connected now to my computer, I can now log in. As I mentioned, 37.3 degrees Celsius is the current temperature of Pi 0, which is the control plane node on my cluster. And basically, you can now go through the setup, assuming you can do the same thing and log into every single node, 1 through 4. In my case, again, Pi 0, Pi 4 to Pi 4 is the host names that I set up for everything. So you can set up to Pi 4. Now is the time to configure Kubernetes. There's one more thing that you have to do when SSHing into each board, and that is because we want to configure Kubernetes, we first need to make sure that the boards, each individual computer in my cluster, can run containers. And to do that, you need to enable cgroups. There are plenty of instructions on the internet on how to do this. your boot file should have something like cgroup memory equals 1 and cgroup enable memory, something like this. It depends on your actual Debian version and Linux version, and but you do have to remember to enable cgroups for your. This is where you see the difference between typing a couple of commands in your favorite cloud console and getting a cluster magically, and actually having to configure everything on your own. So at this point, I'm going to walk you through how I used K3S Up, which is a tool built by Alex Ellis. Go and sponsor Alex if you're benefiting from his work. I'm using K3S Up, which is a tiny tool that connects over SSH to a couple of machines and is able to cluster them together using K3S. Super, super helpful in getting something up and running. You can also do it manually if you want to. There's instructions on K3S on how to do that. You can use other tools and create other kinds of Kubernetes clusters. K3S was very easy for me to set up, as the K3S team did a really good job on the instructions on configuring this on Raspberry Pi cluster, and then K3S Up made the entire setup super, super easy.
Nice.
So
Is it pronounced K3S Up, Radu, or is it
no,
more
it's
ketchup?
not.
Okay.
I have an ongoing beef with how people pronounce tools in the Kubernetes world.
Yeah.
You'll hear me say kube control as opposed to kube cuddle and a whole bunch of others. It's K3S Up. Sorry.
Okay.
I know. Yeah.
But
even though it said ketchup, it's K3S Up for me.
K3S Up. Most people do either kube cuttle or kube CTL. I think you're the only person I met who says kube control, I think. Yeah. the third option.
I used to say kube CTL. It's a mouthful, so
It
kube
is.
control
Kube control. Okay.
kube control it is. So again, shout out to Alex for building K3S Up, building on top of K3S. Basically, the gist of configuring everything with K3S Up is you need to create a JSON file that contains all the machines that you want to configure the cluster with. In this case, Pi 0 to Pi 4, which are the cluster the machines that I set up earlier, and then pass the IP addresses that the local IP addresses, right? It is important to make sure that this is not the Wi-Fi address, because DHCP and ideally these would be static IP addresses that you would configure for each machine. I'm not going to go through any of that right now, but ideally these would be static IP addresses. Because if there are dynamic IP addresses that you get with DHCP, the cluster setup just doesn't know what to do with those. So, and then you can use K3S Up plan, pass the device's JSON file that describes each host with its IP address, and then basically, in this case, I'm saying just one control plane node, and then 4 agents by definition, and then write the script to configure everything in bootstrap.sh. And the output of that is that file being written with the commands to set everything up. And basically, K3S Up install will use the SSH key that was configured when flashing the operating system, and is basically iterating through all of the control plane nodes and all of the host nodes, and basically configuring the K3S cluster. The control plane generates a token, and then each node in the agent pool joins that cluster using the node token. So this essentially is the generated script generated by K3S Up, and then it creates a 5-node cluster. So the output of running this script will be a kubeconfig file that you'll see printed on your console after running the script, and then when you run kube control get nodes, ideally you will see a 5-node cluster, 1 control plane, 4 agents, and that's what I'm seeing here. And for reference, K is what I aliased kube control to, just because I don't want to type kube control every single time, and so it's K. So each node basically has the IP address that was the ETH0 interface. That's basically the Ethernet interface, and these are the IP addresses for every single board. And then you can see that it's running container D. 1.7.11. This is going to be relevant in a couple of minutes. But Debian 12 bookworm, and then I set this cluster up a while back. And yeah, Pi 0 to Pi 4. This is the current utilization of my cluster. Basically, tiny utilization both for CPU and memory. And I have nothing in my default namespace. So before going and talking about SpinKube and how to run WebAssembly on this, anything that people would like to dive into on the cluster itself?
Yeah, folks, if you have any questions, please put them in the chat, about the cluster and the setup a bit. Because yeah, Radu will start with some of the Kubernetes specific things. I want to shout out our friends at Replicated, Radu. They gave us these cool hats when we met them at KubeCon. It says, I think you can see it, it says K8s on it as well. It's a very cool hat. So shout out folks at Replicated. Yeah, nice hats.
Cool.
Yeah, we might get questions later on, Radu, and we'll just get back to it. So
sure. Cool. So recapping, we have a 5-node Kubernetes cluster. It's running K3s. Big shout out to K3s Up project by Alex and K3s in general from SUSE. Really cool way of running Kubernetes in smaller places than usual. And yeah, this is the cluster. Now, the goal of this is to configure and run Spin applications. So we're going to do that using the SpinKube project. Just in case you missed it, SpinKube is a new open source project that basically helps you configure a full stack for running WebAssembly applications in your cluster. Why you would want to do that? Well, they're significantly smaller, more portable, and really dense compute that you can get out of running applications with SpinKube. Entirely open source. It's been submitted as a CNCF sandbox project. So if you're interested in WebAssembly and Kubernetes, please check out the SpinKube project. Last bit in the cluster setup is actually configuring SpinKube. So basically, I just went through the quick start. So there's a documentation article called "Installing with Helm" for SpinKube, and this one goes through configuring your cluster from scratch. First of all, you need to install the SpinKube CRDs. We'll check them out in a second. There are two important ones that we're going to look at, and then a runtime class. And then finally, this depends on Cert Manager. There are a bunch of webhooks that need TLS, and we're using Cert Manager for that. And then finally, we're using still a project called Wasm. The new version of Wasm called Runtime Class Manager is part of the SpinKube project. But essentially, it's a way to configure your cluster to run WebAssembly workloads instead of regular containers, or side by side with regular containers. So it's using the Wasm operator, and this essentially configures each individual node to know how to execute WebAssembly applications. We'll look in a second at what that means in particular, but configuring that is a Helm install. It's using a node installer image that's coming from the SpinKube project, and this one will fetch a container D plugin, a container D shim for Spin, and configure it on your node, and annotate all your nodes to boot up the setup process for the container D shim. You can You can decide here how many nodes you want to actually be able to execute WebAssembly. In this case, I just annotated all of them because I want all nodes to be able to execute WebAssembly workloads. And then last step here is Helm install for the spin operator. So if we go Helm list here, we'll see I have the Wasm operator that's installed in the Wasm operator namespace. I have the spin operator that's configured in the spin operator namespace, and then I have Trafic, which comes built in by default on my installation of K3s, and then I have the Tailscale operator configured, which is a really, really cool project that is able to join my Kubernetes cluster that's running on my desk to my Tailnet, which is my Tailscale network. I'm a huge fan of Tailscale. It makes connecting between devices and computers so much easier. So big shout out to Tailscale. I'm using Tailscale in particular to avoid exposing my cluster to the internet. If I want to like share basically it comes with an ingress controller, which means you can create an ingress with the Tailscale ingress class, and you can have an actual public URL that will eventually point through Tailscale to my Kubernetes cluster, which can expose workloads. So if you're interested in that, I have instructions on how to configure that and join your Tailnet. And then lastly, a bunch of pods that are running. Cert Manager runs its pods, the actual Cert Manager, and then the CA injector and webhooks, and then a couple of kube system pods like metric server and Trafic and things like that. And then I have the Wasm operator, which is listening for whenever new node joins my cluster, it can configure it to run WebAssembly workloads as well. Again, shout out to the Liquid Reply people, Sven and Christoph in particular, who've been working on the Wasm project, now part of the SpinKube project. And then I have the Tailscale operator, which not a requirement for this particular setup. I just really like Tailscale and use it everywhere. And then the spin operator, which is the last bit that brings everything together. It's the thing that's listening for spin applications. So that's the cluster setup. And we are now ready to run some WebAssembly on this cluster. So
yeah, let's do it. Radu, Bunny asks if you've aliased spin to S in your terminal, and if not, why not yet?
Excellent choice. Excellent suggestion.
Thanks, Bunny.
Yeah, I guess I like typing out spin, but not kube control. And I'm not going to dive into why that is. Cool. So, quick recap. I have 5 nodes Kubernetes cluster, and I have nothing in my default namespace, no spin apps anywhere. As part of configuring the spin operator, there are 2 CRDs that get configured on my cluster. One is a spin app, and the second one is a spin app executor. And the executor is the component that actually ends up executing WebAssembly. So we're gonna dive into the containerd shim executor, and at a future stream we'll dive into what cyclotron is and what that all of that means. But for this particular case, we're gonna focus on the containerd shim executor, and that is something that is based on top of the Run Wazi project, which is a project part of the containerd project that makes it very easy to build WebAssembly executors on top of containerd, and this is what makes the SpinKube project possible at the low level execution level. So, and we'll see in a second where that comes into play. So let's let's do a spin U. And I'm a pretty big Rust fan, so I'm going to go with Rust again. Hello, stream SpinKube. And this is what gets configured by default when you do a spin new for a Rust application in this case. Spin.toml and then a simple Rust library. We'll have a look at the spin.toml first. Tiny spin application, a little bit of metadata. And then I have one WebAssembly component that will respond to every single request coming onto this application. It's this WebAssembly component that will get generated whenever I'll run the build command. And then a single function that, as an HTTP request, returns a response and just says, hello, live code Tuesdays. This is SpinKube. Okay. So you can have as complicated of a spin application as you want, and if you're interested in looking at the kinds of applications you can build, have a look at SpinUp Hub, which has a whole bunch of examples and tutorials and samples and templates of applications you can build to run either on your regular spin-off or with SpinKube or Fermion Cloud or anywhere else you can run your spin applications. So in this case, very, very simple application. We'll have a look at a slightly more complicated app in a second. But at this point, you can do spin build to actually generate the WebAssembly component that my app manifest is pointing to. And then just to test that everything is working properly, I can do a spin up. And this is the app that we just built. Main question, someone or I configured SpinKube or someone configured SpinKube for me in a cluster. How do I go from this to deploying that application on SpinKube? Well, we have the answer for you, and that is there's a project part of SpinKube called Spin Plugin Cube, which gives you the ability to scaffold a spin application manifest for SpinKube based on a local application. So you can distribute spin applications using regular container registries, and obviously SpinKube is compatible with that. You can use the exact same registry you deploy your Kubernetes applications regularly, like regular container images. You can use the same registry to distribute your spin applications. And the command to do that is spin registry push. And one more shout out to the replicated people. I'm using ttl.sh, which is a anonymous and ephemeral container registry. You can basically use it as a test registry to push your application for like 24 hours or an hour, and then use it without having to log in and go through the whole dance. Obviously, Spin Registry Push works with all the popular container registries that you can log into. In this case, I'm just using something that's tiny and anonymous, so I don't have to authenticate.
Yeah, at KubeCon, Radu, we did so many demos at the booth, and we used ttl.sh for most of them for the step, and yeah, it just works so well. Right, just such a well made product. Yeah.
Yeah. So this will take the spin application running locally and just push it to my to ttl.sh, and now I can use SpinKube scaffold, and I can pass the registry reference where I pushed my application. Obviously, all of this can be automated in CI. This is how you would do it on the CLI. You can obviously do it on CI as well. But to scaffold my application, you can either pass a mutable tag, or ideally, you would have immutable digests, which is the recommended way to point to artifacts in this world, and then dash show app.yaml. I basically am writing the manifest file to this tiny file. So this is what a spin application looks like. If you ever did Kubernetes before, you'll notice this API version, core.spinoperator.dev. It's a v1 alpha 1 API that indicates this is still an early project that might change. And then this introduces a new kind called SpinApp. It has a tiny bit of metadata for the application name, and then the spec, the image that we just pointed to, and then this is the executor that I mentioned. This tells the spin operator to execute this application using the container D integration. And then you can have things like replicas or image pool secrets or any other configuration supported by SpinKube that we'll look at in a second. This is what the app looks like. We can do kube control apply, and this will take this application manifest and submit it to the Kubernetes API server. And this is where the SpinKube and the spin operator will pick up the application and configure it on the cluster. We can check the status with kube control get spinapps, and we'll see that we have one application called Hello Stream. It desired 2 replicas, which is what we defined in our application manifest. 2 of them are apparently already ready, and this is the executor that was configured. Before going there, let's have a look at what actually get created on my cluster. So spinapps looked at this before. One spin app called Hello Stream, which is what we configured. This also created a Kubernetes service for us, named identically to the spin application. So there's a service now configured called Hello Stream. There's a deployment called Hello Stream with 2 instances, and then obviously the underlying implementation for that deployment, there are 2 pods running in my cluster. So this is how the containerd shim spin executor runs the application behind the scenes. There are a couple of pods, but instead of running regular containers and regular Kubernetes pods, let's have a look at those pods for a second. So these are the pods that are in my default namespace, and I'm just going to pick one randomly on Pi3. And there is one big difference compared to running a regular pod, and that is the runtime class for that pod. This is what tells containerd that this is not a regular container, that this is an actual WebAssembly application, and the runtime class defined at the Wasm project level is called Wasm time spin v2. Spin, as I mentioned, is built on Wasm time, which is the WebAssembly runtime we're using, and this is spin v2 dot something, so spin v2.
Radu, there's a question from Sebastian about the
Yep.
Spin app itself, which is,
Yep.
can the app use Fermion serverless AI, basically, right? Or alternately,
Yes.
could it also use the Spin Cloud GPU plugin?
Yes, that is exactly the next demo that I'm going to show. So I mentioned we're looking at a hello world. Next, we're going to look at an application that is slightly more complicated, and that is exactly what I'm going to show. Short answer, yes. SpinKube and the spin operator supports regular spin runtime config, which means you can point the LLM inferencing service to use like a cloud GPU, the serverless AI inferencing service in Fermion Cloud. You can back your key value store using like Cosmos DB or Redis or something else. So Spin Operator has full support for runtime config in Spin.
Stay tuned.
Yep, that's literally the next sample that I'm going to show. So scribe pod, as I mentioned, this is by all means a regular pod in Kubernetes that is using the new runtime class, which means one more time that the the kubelet and eventually container D is not going to execute a regular Linux container, but instead it's going to execute a WebAssembly application with the Spin runtime class. But the big thing that comes out of this being so tightly integrated with container D and with CRI and with the Kubernetes world is that you can use a lot of the Kubernetes ecosystem for this. So you can pass annotations, you can use, this is an example of an application that uses the horizontal pod autoscaling feature in Kubernetes because we generate regular deployments and services behind the scenes. Because this integrates with something like HPAs, like pod autoscalers, you can use Kata out of the box, and there's examples on how to do that. Um, you can pass image pool secrets if you need to. You can have Kubernetes liveness and readiness probes. You can have more than just HTTP applications. So in this example, I showed a Spin application that was like an HTTP triggered application. It's not you're not limited to just to HTTP applications. This is a sample that uses the Redis trigger, and we have SQS trigger support as well, and other kinds of triggers support coming as well on the SpinKube project. So you can trigger your application not just on HTTP, but based on a whole bunch of different event types. You can define limits and requests for your resources for your Spin application. This is hinting at Sebastian's question. You can define, you have full runtime config support for your Spin application. So if you have the need to declare like SQLite databases and LLM compute for your application, you can define that in your application. This integrates with full Kubernetes secret support. So if you have secrets and passwords and tokens and stuff like that, you can define them and reference other Kubernetes secrets. So you're not exposing those in your spin app manifests. Um, and then
Sam's here,
lastly,
Radu. Sam says hi in the chat. Hey, Sam.
oh, hey Sam.
Nice of you to stop by. If folks are interested in like learning a bunch of Kubernetes things, check out the Cube Simplify channel that Sam and some of his friends run. Really good content about getting started and working with Kubernetes. So yeah, thanks for dropping by, Sam.
And speaking of the LLM inferencing feature that I showed, that I'm going to show in a second, Siam and I did a talk at Wasm.io at the beginning, sometime in March, where we talked about the inferencing feature and showed SpinKube, a SpinKube cluster running in Civo Cloud that was running the sentiment analysis application. So that's already on YouTube. If you're interested in watching that, you can find it on the Wasm.io YouTube channel. And then finally, Spin applications have support for defining variables and configuration. You can define those in your Spin application manifest. You can again point to secrets and things like that. And lastly, because this is regular Kubernetes pods, you can actually do volume mounts and attach storage and persistent volumes to your Spin application. So your Spin application has access to things like Kubernetes volumes. So if you're interested in compatibility with a lot of the Kubernetes ecosystem, the SpinKube project, and in particular because of the container D integration, means you can do things like sidecars and init containers and volume mounts and liveness and readiness probes and a whole bunch of Kubernetes integration points, because this is very, very tightly coupled with Kubernetes. So yeah, as I mentioned, this ends up generating a Kubernetes pod, and this is you can continue to monitor that as you would normally. And lastly, we can actually look at the application that's running. So let's go to pick one of the pods, and we can see, yep, our application is up and running and listening. This is the available route, the Hello Stream SpinKube component that we configured, and I'm gonna give a shout out to Rajat from our team who built a tiny kube control plugin that does a reverse proxy. You can do kube control port forward or kube control. This is a way to basically check that our application is live and up and running in the cluster. So as I send requests, you can see the two different pods that are load balanced when handling my application, and that's because I have two pods that are serving my application. So I'm going to move this over in the lower pane. And one of the things that I really like about the plugin that I just shared that Rajat built is it gives you a graph of the available instances that are there to serve your application. So in this case, we have two instances of our app. What I'm going to do is just do 5 and have a look at what's happening in the cluster. It should be up to 5 now. And let's go back to 1 for a second. Okay, so we have one instance of our app configured. The main thing that I'm interested in at this point is this is the artifact. This is the entire application compiled into a 1.9 megabyte file. We can get this down to like significantly smaller size, but I literally just did a hello world and didn't optimize it at all. It's about 2 megabytes, but that's a full contained self-contained application. Now, because it's not a full Linux file system and not a full container, what I would like to do and what I'm expecting to see is it scaling up to say 50 instances much faster than like say fetching a 200 megabyte container would. So let's try and scale this to 50 and have a look at what's happening. And this is the instance count available in my cluster for this particular application, and it's at 50, like it's there in a couple of seconds. So imagine hooking this up to a horizontal pod autoscaler or something like Kada, and basically scale based on incoming traffic or queue size or uh, how long it takes to handle requests. And basically, once you handle all the incoming traffic, you can scale back down to 0, and that's about it. And then remember, all of this is running on this tiny cluster, right? So this is not a beefed up cloud cluster that's running like tens of cores. This is a tiny 5-node Kubernetes cluster that is running Spin applications. And we could try and go slightly higher. So let's do 100.
Before we do that, Radu, I think we have
Yes.
a question. So one,
Yes.
hey, Teddy Bear, nice name. Thanks for dropping by the stream. Question from Bunny, which is, there's no such thing as a tangential question on the live stream, Bunny. Feel free. Are there any Fermion grapes keeping an eye on Modular's Mojo programming language? No Wasm compiler yet, as far as I know, but Rust and Python had a baby, seems promising. So, Radu, you're like a resident sort of what's the latest and greatest in tech. I keep up with all the latest stuff through Radu on our internal Slack. Have you tried it, Radu?
I've not tried it, but I've been watching the Mojo language for quite a while. One of the main reasons why it's a very, very interesting project is because the main person who built it has been working on things like LLVM and Swift for a very long time. So this is as serious of a programming language and project as it gets. And I think they recently open sourced their standard library, which is a nice step. I haven't tried it yet, and I'm not up to date on their WebAssembly plans if they have them at all. I don't think they do have them yet. But their goal of being compatible with the Python ecosystem is really, really cool. Partly because with the componentized Py project, we can actually compile, like using the CPython project, compile Python and run it in Spin and in Wasm time. I think you and Joel had a session on componentized Py recently. So
Yeah, we
shameless
did.
plug to go watch Joel's session. But this is a very interesting kind of new programming language built from the ground up with a very, very clear goal in mind. And I'm very, very curious to see where it leads and what happens with all of the machine learning world. Rust and Python had a baby is is a very, very funny way of describing the language.
Yeah, yeah. And if anyone in the audience has either tried it out or has thoughts or opinions about it, yeah, feel free. As Radu said, I only know of this through like reading about it on like Hacker News and stuff like that, but haven't actually tried it out. Yeah.
Cool. Okay. Let's we're at one instance of our app. Let's try and bump this to 100 and see what happens. It's going up. It's at 80-ish, and now it's at 100. And essentially, you can, because this is so fast to start, and there are a bunch of optimizations that we're in the process of doing to container D and to the shim in particular. This will be even faster in the future, but because you're only supposed to start a 2 megabyte application that is heavily optimized, it's already machine code by the time it gets the request to run it on the shim. This is very, very fast to start up and equally as fast to just to go down. So this is this resource utilization of the cluster that's running those get spin apps with 100 deployments. Like, this is not consuming anything because there's really not a lot of tiny memory and CPU footprint from just scheduling those. And then going back to one, and again, each of those instances is capable of executing a lot of concurrent requests. So think about it as application servers, and you scale up when you need to handle more incoming concurrent requests, and then you scale back down when you need to handle fewer concurrent requests. But each of these, depending on how many resources you assign, can handle tens of thousands of concurrent requests. So think about it as regular application servers. And one more time, because this integrates with horizontal pod autoscalers and Kata and autoscalers in general, you can hook this to automation. And if you're interested in seeing a real use case for this, like a couple of weeks ago, Kai and Florian from Zeiss showed their setup on how they're prototyping all of this for their order processing system that is actually hooked in with Kata and Dapper, and you can find all of it here. So if you go to samples, spin Dapper TypeScript, this basically shows a full setup of how you can configure a spin application with Dapper, with Kata, with autoscaling, and tweak it to the point where you have the best efficiency compared to performance that you can get out of this. So have a look at this as well.
Yeah, shout out. And Ancient IT Guy on cue also says, "Hi guys, this show is now my favorite Tuesday closing of my workday." Thank you so much, Ancient IT Guy.
Nice.
Yeah, glad that you can stop by. Radu, if we could go back to the terminal, and you showed the performance with the memory and the memory usage, right?
Yes.
So the P0, of course, is the control plane, but even the
Yep.
others, am I right in assuming that a lot of that memory usage is just like the bells and whistles, like the container and all of that that's happening, as opposed to the spin apps that you're running?
Let me scale it back up now,
Mm-hmm.
and I'll SSH into a node and show all of that.
Yeah.
Okay. What's happening here? Okay. Let's wait for this to go back to 100. There's a bunch
There's,
of
sorry, I have to just shout this out loud. It's crazy that this happened, but the number of viewers on our StreamYard hit 100 as soon as you did that. It's too much of a coincidence.
Yay.
Yeah.
Cool.
Yeah.
There's a bunch of memory that Pi0 gets taxed on. Oh, there, it's back down now. Pi0 is the only control plane node, which means whenever you do a whole bunch of Kubernetes API server operations, it is the one that has to handle all of them. But now it's back down. Let's try and do SSH Pi at. Let's pick a random one. Let's pick 3. I have no idea what's running on this. But yeah, K3s, you can basically look at all the processes and the shim processes that are running as part of this, and you can look at the memory that's being used by all of that, by any of those memory percent, like 0.4%. There is a whole discussion around real memory usage on Linux that I'm not going to get into. I'm just going to use the numbers that the Kubernetes API server reports, and that is like uh, something along like 15% memory utilization.
Mhm.
You can dive into and see exactly who's consuming what here, but eventually, yeah, every application has a tiny memory footprint, uh, and then yeah, there's regular Kubernetes overhead because of pause containers and other things, but you can actually dive into the node and see what's happening. Realistically, yeah, the K3s agent, the Kubernetes kubelet, is the one that's consuming most of the resources here. So you can see there. Spin apps. Let's go back down and do one. Actually, let's delete the app altogether. Cool. Now, as Sebastian hinted at, because this is a place to deploy your regular Spin applications, it has support for configuring your app and exactly how you would expect when running your Spin application everywhere. So this is the Spin application that is from the AI examples that we have in the Fermion GitHub org. It's the sentiment analysis TypeScript application, and this is essentially a tiny application with 2 components that and a UI that you can use to do sentiment analysis on some random text. So this application has a sentiment analysis component, which is the API, and then a UI that connects to the API. So the API is the important bit. A little bit of this is using Llama 2, so it's a little bit of a system prompt of telling the model what it's supposed to do, and then perform sentiment analysis. Now it's using key value, and it's using LLMs. So if you look at the spin.toml, this application from the guest from content is not allowed to access any network host. It's allowed to use a default key value store, and we'll explore in a bit what that is. And then it's allowed to use a Llama 2 chat model. So if you were to run this application locally, tree.spin, you would have to provide a Llama 2 chat model. In this case, if I want to run it locally, I can point it to like Llama 2 7 billion chats. I'm not going to run it locally because it's going to take a bunch to execute. Uh, but as Sebastian hinted at, um, cloud GPU spin Cloud GPU. Yes, there's a plugin called SpinCloud GPU that lets you basically connect your Spin application that is trying to do language models and AI inferencing to execute the inferencing on Fermi Cloud, where we have GPUs, and that's done with a tiny bit of runtime configuration. So I can do spin up and point to a runtime configuration file, and now I have the application running locally, except for the sentiment analysis operation. So this is my first live stream, and it's apparently a positive sentiment. This is really bad. And this is a negative sentiment. So because of the portability of how Spin is able to work with and build WebAssembly components, you can satisfy that import, that inferencing operation, either locally or depending on configuration, with something like the Fermion serverless AI inferencing service. So because this application requires runtime config, I'm going to remove this token right after the screen. But basically, this is the kind of information that you would need to configure. This is what I passed to the spin up operation. So whenever trying to execute LLM compute, use the remote HTTP. This is the application that's running in Fermi Cloud, and this is the auth token for it. And I went through the process of doing the same thing here, like SpinKube scaffold. And I have a Spin application that looks very, very similar to what we had before, like Spin operator, V1 Alpha 1, Spin application, some metadata, image in ttl.sh, and then I have a runtime config field that's pointing to LLM compute, and this is literally the same runtime config file information that I had previously. As I mentioned earlier, you are strongly encouraged to instead of pointing and having secret variables in your application manifest, to point those to Kubernetes secrets. And there are examples on how to do that here. I wanted to show that there's nothing hidden there. And you can literally just pass the LLM runtime config as you would in a runtime config file locally. Because this is integrating with actual Kubernetes secrets, you can use whatever KMS system you might already have in your Kubernetes system. So if you're using like Vault or your cloud provided key management service or secret service, you can just use that here as well. In this case, I'm doing the horrible thing of pointing to tokens directly in my application manifest file. So regularly I do a kube control apply, and I now have my sentiment analysis app that's running in my cluster in exactly the same way as before. These are the scribe pods. This is regular Kubernetes pod with a runtime class that means is running the with the container dshim, and now I can do k reverse proxy, and I can do sentiment analysis, and I can go to localhost 1990, which is where I'm proxying the requests, and I have the application running here. SpinKube is a really cool project, and hopefully this will work and connect to the LLM inference service in Fermion Cloud, and then pipe the result back in. All of it while running on my tiny cluster on my desk here. Because this cluster has no hardware acceleration, it has no GPU, it has no compute graphics compute device, it would take a really, really long time to run like a llama model on this. It's possible, it's absolutely possible, but it's really impractical in this case. And so this is why we're showing the configuration of how to run the application here, but use the GPU power from elsewhere, basically. Yeah. this is the app running here.
Sweet. Yeah, early on, Seb asked a question about running Fermion serverless AI or speaking with an LLM through SpinKube. And yeah, it is possible, as Radu showed. I put a bunch of links in the YouTube chat if you just want to check out either the sample, the Cloud GPU
Yep.
plugin, or just SpinKube in general. So yeah, you can see the activity in the Cloud UI as
Yeah.
well. Those are the requests made to the large
Yeah,
language
and
model.
these are the they'll the confirmation that it's actually running on this A100 GPU that's somewhere in Fermion Cloud. Shout out to Siam and Civo Cloud for providing the GPUs for this.
Yeah, I mean, so I think just to sort of recap here, Radu has a cool Pico cluster there with Raspberry with 4. No, do you count the master plane as well, the control plane? Yeah, so 5.
Yeah, it's a 5-node
It's a
cluster.
5
Yeah.
node, it's a 5 node cluster running. And yeah, there was K3s installed, and SpinKube was installed on that. We played around with spin apps, so we were able to scale up to like 100 spin apps running there. And yeah, that was the demo. Anything else, Radha, you want to share? Oh, you had to share the gist as well, the link to the gist, so that if people want to set it up on their own Raspberry Pis, perhaps.
There will be an article coming up on fermion.com. I'm not sure if I can share this here. Nope, I'm not able to.
That's okay. We know we've been pushing Radu to write a blog on the Fermion blog as well, so you'll get that soon enough. But if you have any trouble, just come back to the stream.
Gist.github.com and my username, you'll find it here. It's public.
Okay.
If do we have the time to dive into like how all of that is actually executed on the containerd on a random node, or do we keep that for a future stream to keep people what do you think?
Yeah, I mean, we're 10 minutes over our usual time, so maybe we can wind down, but yeah, I think that's a good idea for a future stream, Radu, where we talk about that.
If people are interested, I'd be happy to dive into the low level containerd shenanigans that are happening on the node and how that's running, and how you can run with CTR and handle that locally and manually pass the runtime class, and dive into pre-compilation and ahead of time compilation and how all of that works with the containerd content store. And I'm trying to get people excited.
You said
about that.
you said all the right things. So definitely,
I said all the words.
You said all the words, yeah. Sebastian also said there will be a V2 of his soon-to-be released blog post that uses Fermion's AI and Redis as memory for a chatbot. So yeah, that's very cool. Sebastian was working on a piece where he sort of got Fermion serverless AI and Redis running for a chatbot. It's on his. I think it will be published soon, if I'm not mistaken, on IT Next. We're still waiting for the publication. And yeah, great to hear, Sebastian, that SpinKube's running on your Civo cluster as well. Yeah, that's awesome.
Side note, if you are running on Civo, there's an add-on in the marketplace for SpinKube. So when you create a Talos Kubernetes cluster on Civo, you can literally just add a check mark next to SpinKube, and you can configure it directly on your cluster. Big shout out to Siam who configured that integration.
Yeah, big shout out to folks at Civo. And yeah, thank you everyone for joining in. Everyone from Sebastian, Bunny, Kai, Teddy Bear, Siam, Rajat, Adam, Vamshi, Nuno, everyone else as well. Yeah, we do this every week on Tuesday at 5 p.m. CET. So yeah, join us next week as well. Our next week is TBD on what the topic is. We're still waiting for a couple of confirmations. But in the next few weeks, we have people from SUSE, AKS. We have a special guest talking about Zig as well, which if you're interested in a new cool programming language, that would be cool as well. And yeah, join us again. Nice to see Frank here as well. Frank, thank you so much for stopping by on our stream. And yeah, hope to see you all next week. Thank you, Radu, so much for this. And everyone else, watch out for the blog post about how Radu actually built this out.
Yeah. if people are interested, I'm happy to dive into over on Discord or in the CNCF Slack about any of this. And if you're interested in running a lot more than hundreds of apps on a spin apps on a Kubernetes cluster, we might have something for you. So
Yeah, just call us.
yep.
All right, folks, that was fun. See you again next week. Thanks again, Radu. Thanks, everyone. Bye bye.